In section 4.1, we begin our discussion of probabilities. Probability is a section of this topic of statistics that is unique but also finds itself becoming important as we dig into other statistical topics, primarily when we get to things such as hypothesis testing and confidence intervals. We'll see what that looks like a little later in this course. But section 4.1, what we're going to do is we're going to begin to define what we mean by probability and to define some of the terminology that we're going to use. So we have this: a probability experiment is a chance process that leads to well-defined results called outcomes. And an outcome is the single result of a single trial of a probability experiment. Okay? And then thirdly, a sample space is the set of all possible outcomes of a probability experiment. So let's actually look at some examples to see what we mean by those three things. Let's take a look at this box right here that outlines four different probability experiments. Well, the first probability experiment is tossing a coin, right? So that is a chance process that leads to a well-defined results, and each of those results we call outcomes. Okay, so the probability experiment is flipping a coin. The outcomes are either head or tail. The sample space is all the outcomes combined. So head and tail combined give us our full sample space. In other words, the sample space is what are all the possible outcomes? Well, heads or tails. There's no other possible outcomes with flipping a coin. What about this next one, rolling a die? Well, we know that the possible outcomes are 1, 2, 3, and 4, and 5, and 6. So those 6 numbers make up our sample space. The probability experiment is actually rolling the die. The outcome is, what number do we end up getting? So we got another one here, an answer to a true or false question. Well, what's our sample space? Our sample space is all possible outcomes. Well, true or false, it's either going to be true or it's going to be false. Those are our two outcomes that create our sample space. And lastly, this is an interesting one, tossing 2 coins. Look at what they have here. One of the outcomes is that each coin is a head. Another outcome is that each coin is a tail. Another outcome of tossing 2 coins is that the first coin is a head and the second coin is a tail. So that's our third outcome. We do have one fourth outcome right here. It's that the first coin is a tail and the second coin is a head. So I've got 4 different unique outcomes for the probability experiment of tossing 2 coins. And all 4 of those outcomes make up my sample space. One more example to see how, not complicated, but how this can be applied to some unique scenarios is rolling 2 dice. Okay, find the sample space for rolling 2 dice. Since each die can land in 6 different ways, the 2 die are rolled. The sample space can be represented by a rectangular array as shown in figure 4.1. The sample space is the list of pairs of numbers in this chart. So we know that a die has 6 sides, 1 through 6. But if I'm rolling 2 different dice, you've probably played many different games where you've had to roll 2 dice at the same time. Right? Well, I know I can get a 1 and a 1, or a 1 and a 2, or a 1 and a 3, or a 1 and a 4, or a 1 and a 5, or a 1 and a 6. Okay? That's if my first die gives me a 1, and then all the other possibilities of what the second die gives me. Well, what if the first die gives me a 2, combined with all of the different possibilities that die 2 could give me? you can see where we're going with this and why it's a 6x6 grid, because the first die has 6 different outcomes. The second die has 6 different outcomes. Pairing up all of those in each way possible creates 36 different outcomes that make up our sample space for the experiment of rolling 2 dice. So that kind of gives us a structure and a framework for what we're talking about when it comes to probability. Let's begin to take a look at things a little more in depth. Because here's a unique scenario. Okay? It says this: use a tree diagram to find the sample space for the gender of 3 children in a family. Well, if I'm looking at 3 different children, it's a little difficult to make a chart where the column represents one of the children and the row represents another child. Where do I put the third child? Right? So in order to figure out the sample space of an example like this, we're going to use what's called a tree diagram. A tree diagram is a device consisting of line segments emanating from a starting point and also from the outcome point. It is used to determine all possible outcomes of a probability experiment. So here's how this works. I've got 3 different children, and I want to figure out what are all the possible genders of those 3 children. So what we're going to do is we're going to start at, notice what a tree diagram says it is, it's starting at a point. So here's the point that I'm going to start from. Now, I am going to have the first child. And that first child is either going to be male or female. Great. So this is child 1. Okay. But we know we're not just going to have one child, we're having 3 children. So what are we going to do? Now let's look at child 2. Child 2 is going to branch off of each of the outcomes of child 1. But again, what are the possible outcomes? Male or female? Again, male or female. This is child 2. So what is this communicating so far? It's communicating that child 1 could be male, and then child 2 could be male, or child 1 could be male and child 2 could be female. Or child 1 could have been female, and then child 2 male, and lastly, child 1 could be female, and then child 2 could be female. So we're starting to see that if we follow each of these branches, it shows us the different possible outcomes of 2 children. But we actually are not looking at only 2, we're looking at 3 children. So what are we going to do? We're going to branch off of each of those outcomes yet again. And what are our 2 possible outcomes for child 3? Male, female, male, female, male, female, and male, female. And what we have now here is a branching from a tree diagram that shows us all possible outcomes of the gender of 3 children. This top one, male, male, male. What do we now have? Male, male, female. The next one, male, female, male, male, female, female. Now I have female, male, male, female, male, female, 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 male, and last but not least, female, female, female. So these are how many do we have? These are the 8 different scenarios that exist with the possibility of the genders of 3 different children. Now, here's where we do need to add one more, vocabulary word. It says this: an event consists of a set of outcomes of probability experiments. So the reason this comes into play is that an outcome for us would be either the child is a male or female. But we're not just interested in the outcome of a single child. We're looking at the combination of the outcomes of 3 different children. We call that an event. So getting a female, male, female, right here, this is an event. Right? It consists of a set of outcomes of a probability experiment. Okay. Now, added on to that, we have these 2 ideas of a simple event and a compound event. Okay. If we, let's consider really quick rolling a dice when it comes to what we mean by a simple event and a compound event. Okay. Actually, no, let's use this example up here that we have right here. A simple event would be something to the effect of, let's look at this event right up here, male, male, male. Okay. Are there any other events in my sample space here that produce that same result? No, not really. Nope, there's only one. It's that male, male, male right there. Okay. So we would call that a simple event. Okay. Well, what about a scenario? Take a look at this. What if I'm looking at, let's look at male, male, female, or male, female, male. In each of those, I have 2 males and 1 female. In fact, I've got 2 males and 1 female right here as well. We would call getting 2 males and 1 female a compound event because it happens in multiple different scenarios. Now, the ordering is different, right? But the event of getting 2 males and 1 female, okay, exists with several different combinations. So simple event, compound event. So this gets us into our discussion of what is called classical probability, where we want to define how we're going to do probability from here on out. So classical probability equals, let's first approach it from this vocabulary phrase right here. Equally likely events are events that have the same probability of occurring. That's going to come into play here in just a moment. Take a look at this, the formula for classical probability. The probability of any event E is what? The number of outcomes in E over the total number of outcomes in the sample space. But then we have this notation right here that we want to get in the habit of using. This probability is noted by P of E equals N of E over N of S, where N of E is the number of outcomes in E, and N of S is the number of outcomes in the sample space S. So let's do this. E represents the probability event, okay, of an event E. I'm going to say that that E for me is equal to rolling an even number on a die. Okay, so I'm going to roll a dice, and the outcome, the specific outcome, there's a lot of different outcomes, but the specific outcome that I'm interested in is rolling an even number on the die. All right? So what I want to do is I want to find the probability of E. So the probability of E is going to equal N of E over N of S. Well, what does N of E equal? Well, N of E is the number of outcomes in E. Well, on a dice, if I roll it, how many of the sides of the dice are even numbers? Now, there's the 2, the 4, and the 6. So, 3. 3 of the outcomes fit into the event E of rolling an even number. All over, what is N sub S? N sub S is the number of outcomes in the sample space. Well, how many different outcomes are there that make up the sample space for rolling a die? 1, 2, 3, 4, 5, and 6. There's 6 total outcomes. So P of E equals 3 out of 6. 3 of the possible 6 outcomes achieve my event E of rolling an even number. Great, we can reduce that. 3 over 6 is 1/2. So this is the way that we write and think about classical probability. Here's a side note. Probabilities can be represented by fractions, decimals, and percents. So that fraction that we got up there of 1/2, as a decimal, we know is 0.5, and as a percent, we know is 50%. So each of these, when it comes to probability, are equivalent to each other. We can represent a probability as a fraction, as a decimal, or as a percent. Well, let's take a look at a few more examples of this so that we can really get our understanding of how to operate with probabilities settled. Drawing cards, find the probability of getting a black 6 when one card is randomly selected from an ordinary deck. Okay, so E for us is equal to a black 6. Okay, so what is the probability of E? Well, we know the probability of E equals, well, how many outcomes fit into that event E? How many black 6s are there? Well, I know I have 2 different suits that are black, the spades and the clubs, and each of those has a 6. So there are 2 different cards in my deck of cards that fit the scenario or fit the outcome of black 6. Out of, well, how many cards do I know I have in a deck? I know a deck of cards contains 52 cards. So 2 out of 52. I can reduce that to 1 out of 26. And we can leave that as a fraction. So what's the probability of randomly selecting a black 6 from a deck of cards? 1/26. Great. Next example, if a family has 3 children, find the probability that exactly 2 of the 3 children are boys. Oh, let's do this. We just did the tree diagram that illustrates that. 3 children. We want to find the probability that exactly 2 of the 3 children are boys. Let's go back up to that tree diagram that we created. 2 of the 3 children are boys. So first off, okay, the event that we're worried about is the 2 out of 3 are boys. Well, let me just go ahead and circle. Here's 2 out of 3 that are boys. Here's 2 out of 3 that are boys. And here's 2 out of 3 that are boys. So how many outcomes fit the event of exactly 2 of the 3 children are boys? So P of E is equal to 3 over, right, because the top number is how many events fit that scenario, over what are the total number of events in my sample space. If I go back up to my tree diagram, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different events that exist. So 3 over 8. Excuse me. So the probability of exactly 2 of the 3 children being boys is 3 out of 8. Great. Now let's go back to looking at a deck of cards. It says a card is drawn from an ordinary deck. Find the probability of, we got 3 different examples here. A heart. Okay, so let's call this event A. Let's call getting a black card event B. And let's call getting the 8 of diamonds event C. So what is the probability of event A? Okay, what is the probability of a heart? Well, I know that a deck of cards is 52, split up into 4 equal suits of 13 cards each. Hearts are one of those suits, so I know that there are 13 hearts that exist in a deck of cards out of a total of 52 cards. If I reduce that, that ends up being 1/4. Or let's represent that as a fraction or as a percentage. 1/4 is the same thing as 0.25, which is the same thing as 25%. So what's the probability of getting a heart when you randomly select a card from a deck of cards? 25%, or 1/4. What about the probability of event B, getting a black card? Well, I know two of the suits are black. Each suit is 13. That means I have a total of 26 cards that are black out of my 52. 26 divided by 52 reduces to 1/2. So what's the probability of getting a black card? 1 out of 2, or 50%. Lastly, what's the probability of event C? Event C is the 8 of diamonds. Well, there's only one card that is both diamond and an 8. So that's going to be, there's one possible event that gives me an 8 of diamonds out of the 52 possible outcomes in my sample space. Well, that doesn't need any reduction. It's already reduced. So what's the probability of getting an 8 of diamonds? 1 out of 52. Great. So, a couple rules of probability. Okay, the probability of an event E is a number, either a fraction or a decimal, between and including 0 and 1. Okay? This is actually fairly important because 0 represents 0%, 1 represents 100%. Okay? Notice fraction or a decimal. We know that let's say, excuse me again. Okay, we know that anything greater than 1 as a fraction represents something more than 100%. Is it possible to have an event that has more than 100% chance of happening? Well, we know just logically, no, that can't happen. Or what about less than 0%? Is it possible to have an event that is negative 10%, that has a negative 10% chance of happening? No, that doesn't even logically make sense, right? So we know that all probabilities are between 0 and 1 and including 0 and 1. Or another way of saying it is between 0% and 100%. Here's the other interesting one. The sum of the probabilities of all the outcomes in a sample space is 1. In other words, the sum of all the probabilities of all the different outcomes in a sample space, they all add up to 100%. Okay? Number 3, if an event E can't occur, its probability is 0. That makes sense. Number 4, if an event E is certain, in other words, it is absolutely going to happen no matter what, the probability of E is 1, or 100%. So a couple rules that seem pretty self-explanatory, but it's really important for us to define those so that we're all working from the same set of understanding. Another example, or another concept here, is the complement of an event E. Formally, it's the set of outcomes in the sample space that are not included in the outcome of event E. The complement of E is denoted by E bar. Here's what this simply means. The complement of E is the exact opposite of E happening. Excuse me. So for instance, if I said that E equaled getting a heart when drawing a card from a deck of cards, E bar would equal not a heart. So that would be getting a diamond, a spade, or a club. Now we have a couple different rules for complement events. The probability of E complement or E bar is equal to 1 minus the probability of E. Now, hopefully that makes sense, and each of these is just rewriting those in a different way. I know that the probability of getting a heart is 13 out of 52. Well, I know the probability of E bar, the probability of not getting a heart, is 39 out of 52. Well, if I add those two up, 13 over 52 plus 39 over 52, guess what I get? 52 over 52. I get 100%. So that's what that rule is essentially illustrating. Taking a look at an example of that really quick. In a study, it was found that 24% of people who were victims of a violent crime were aged 20 to 24. If a person is selected at random, find the probability that the person is younger than 20 or older than 24. In other words, they're not between ages 20 and 24. Well, if I know that 24% were between that age, what is 1 minus 24%? Well, it's 76%. So the outcome or the probability that it's not that it's younger than 20 or older than 24, that is the exact opposite of between 20 and 24. So I know I can simply take the probability of 24% and subtract it from, I'll rewrite this so that I'm in percentage, subtracting it from 100%, or 1 minus 0.24 is equal to 0.76. Two different ways to look at it, one as percentages, one as fractions. Last thing we need to talk about really quick, two different concepts: empirical probability and law of large numbers, and they're somewhat related to each other. Theoretically, what do we know about the probability? Let's say that E equals flipping a coin and getting a tails. Okay, theoretically, what do I know the probability of getting a tails when I flip a coin? Well, I know it's 1/2 because it's one outcome out of two total outcomes in my sample space. Okay? But what if I did this? What if I flipped a coin just at random, and I actually did this empirically, meaning I did an experiment, and I got tails, heads, tails, tails, heads, tails, heads, tails, 4, 5, 6, 7, tails, and tails. Okay, I just flipped a coin 10 times, and these are the outcomes that I got. Well, if I were to find the probability of getting a tails from my empirical data from my experiment, well, how many tails did I get? I got 1, 2, 3, 4, 5, 6, 7. 7 out of the 10 ended up being tails. Well, that means that the probability of flipping a tail from a coin is 70%. Well, we know that that's not true. Right? We know that it's 50%, right? So that's the concept of empirical probability. Empirical probability is probability that's gained from actually conducting an experiment rather than understanding it theoretically from what we know to be true logically. But here's the thing, and how empirical probability and theoretical probability are connected. They're connected through this concept of the law of large numbers. Okay? The law of large numbers simply says this: if you increase the number of trials in an empirical experiment, your empirical probability will slowly but surely get really close to your theoretical probability. Here's what this means. If I only flip a coin 10 times, we all know we're not going to get exactly 50 heads or 50% heads, 50% tails. But what if I flip a coin 10,000 times? If I flip the coin 10,000 times, what's going to happen to the number of tails and the number of heads that I get? They are slowly but surely going to start evening out, where half of them are heads and half of them are tails. Because what's interesting is this. Let's say that out of the 10,000 times that I flip it, notice that I had that there was 3 tails and I'm sorry, 7 tails and 3 heads. That's a difference of 4. All right, so what if I had 4,998 heads, and tails I had 5,002? Well, that equals 10,000, those two numbers together, right? But 5,002 tails over 10,000 total flips is equal to something really, really close to 1/2, right? So a difference of 4 between how many heads and tails there are when you're only flipping 10 times compared to when you're flipping 10,000 times makes almost zero impact in the long run. So the more you run an experiment, the closer the probabilities of your events or outcomes in your experiment will get to what we know the theoretical probability is. So there's your introduction in section 4.1 to what probability is. In the next sections, we're going to refine things and apply them to different scenarios.